Hello, I present to you a presentation about cyber physical systems. This one is high level design of a home autonomous system based on cyber physical system modeling by me, Matyas Yimeshi. This is for 6263, which is the cyber physical systems course at Georgia Tech. I'd like to acknowledge that what I'm presenting here is originally done by these people here, Basman M. Hassan Al Hafid. I'm not sure if I pronounced that right. Um, from the Florida Institute of Technology, the University of Mosul, Iraq, and also William H. Allen, also from the Florida Institute of Technology. This was presented at the 2017 IEEE 37th International Conference on Distributed Computing Systems, June 5th to the 8th, Atlanta, Georgia. The original research paper is linked here at the bottom if you'd like to give that a read. Essentially, this paper is about a kind of abstract design pattern for Internet of Things, cyber physical systems scenarios. So let's say you want to build a bunch of new houses. Well, with Internet of Things technology, if you're concerned with cyber physical system security, which anyone should be, then this design pattern should resolve a lot of the challenges that would be encountered. The Internet of Things industry generated over 237 billion in spending in 2017. Internet of Things can be useful for many different physical applications. It's important to plan the security of such a system since it monitors users' behaviors in order to function conveniently. Cyber-physical systems are engineered systems that are built from and depend upon the seamless integration of computational and physical components. With such a wide definition, it's more of a type of perspective of engineered systems than a definition of them. A goal of cyber physical systems is to better understand the physical world, to the end of improving intelligence, understanding, and mitigating the limitations of the physical world. So, with creating an abstract kind of design pattern for Internet of Things, cyber physical systems layouts, it helps to categorize the challenges, first of all, that you're going to be facing. Portability, timing, predictability, and integrity are the desired traits of any such system. Stepanovich identified heterogeneity, or diversity, as one major problem that developers face in real-world applications, particularly for Internet of Things applications. Users of smart home technology can have very different needs. Timing. A proper timing analysis must occur prior to and during implementation of such systems. Connection problems. This covers predictability and integrity. Connection problems can wreak havoc, especially on real-time systems. This problem must always be minimized. Here is the proposed design pattern, a very high-level view of it. An intelligent agent referred to as the butler is shown overseeing 9 other agents shown in the figure to the right. The storage agent has sole communication with the cloud servers, which we'll get into a little more in following slides. It talks only to the butler, healthcare, grid tie renewable energy, security, and weather subsystems. The storage agent does not get accessed by all of the subsystems. This makes sense. You want vital information backed up like health and security. Renewable energy statistics are important to gauge your energy needs. Of course, the butler has direct access to every subsystem, a common and practical choice for an executive type system. We also propose a 5C architecture. That is 5 things that start with the letter C. How convenient. To be flexible to different demands, the first 3 software layers in the 5C architecture should be analytical and flexible for other layers. The 5C architecture helps ensure a smart home will be autonomous, intelligent, and have adaptable abilities. A user will interact most directly with level 5, the smart connection layer. Levels 3 through 5 exist in the home, while levels 1 and 2 are provided by third-party cloud services to ensure that a seamless interface of smart homes can interface with a grander scale of smart cities. So this kind of abstract view is very similar to networking, where you'll have different network topologies that abstract ones and zeros to packets of data that a user might be more understanding of versus what a computer layer kind of thing might be more understanding of. Whereas in the 5C architecture, this is more of still, with the user in mind at the smart connection level, and more of the system itself in mind with levels 3 through 1 in particular. So let's talk about the butler. Of the 9 agents the butler communicates with, 8 are subunits which have nodes, but exclude the storage agent. Nodes are defined here as sensors, actuators, and devices. For example, the lighting subunit controls all lighting devices. These lighting devices are part of the Smart Connection Level 5 of the 5C architecture. By having subunits act as the data to information layer of the 5C, or APIs, for groups of devices, the system is made portable. The butler is the cyber level. It tracks the user's behavior continuously, handles communication and storing of data via the storage agent. So the storage agent is a bit trivial. The cloud computing aspect of it is not so important to the user as the sensors, actuators, and devices of the other subunits. Obviously, if the storage agent were to have an error, the user would be informed by the system that it had some sort of a fault, as it would with any other subunit. But for the purpose of discussion, the other 8 subunits here are the focus. So here is a diagram of the security subsystem. The security subunit connects all security sensors, actuators, and devices to the security subsystem agent. The agent monitors and controls all security nodes, buffering, reading statuses, running commands, data mining, and context processing. This data is then passed along to the storage agent, which can communicate with the cloud and the butler. The cloud stores machine-generated data to drive insights through analytical tools via third-party services. The butler stores and views the data, administers nodes and agents, configures rules, alerts, and performs other actions using out-of-box or custom portals through data analyzing, status reading, command ordering, learning, tracking, and adaptation. The butler oversees a lot of different things that are going on and does the bulk of the processing. Let's look at the lighting subsystems agent. Now that the security subsystem has updated data and has been pushed forward to the intelligent agent in the cloud, the lighting agent monitors and controls all lighting nodes, buffering, reading statuses, running commands, data mining, and context processing. The lighting subunit connects illuminance sensors, actuators to the security subsystem agent. So now that it has all that data from the butler and the cloud, the security system might say, hey, turn off the lights if someone breaks in. The lighting subsystem responds. All of this communication handled by the intelligent agent based on its own interpretation of the situation and to some degree what's going on at the layers 1 and 2 of the 5C architecture, the cloud computing aspect of it. More on the subsystems and the butler. Each subsystem has exclusive access to its own nodes. The security subsystem, for instance, has a motion detector, smoke detector, ability to lock doors, window detector, and camera stream. Each subunit has many unique tasks. The security system may monitor and control nodes, buffer and send its status to the butler, perform actions requested by the butler, or perform data mining and context awareness background processing. The butler handles learning the user's habits, and the storage agent has exclusive access to the internet. The butler handles tasks delegated by the user in 3 phases of automatic mode: initialization phase, learning phase, and action phase. The initialization phase sets up all of the subsystems and their nodes. In the learning phase, the statuses of all nodes are gathered. A decision is made to generate a hypothesis of the set of inputs. If it's a new set of information, the butler waits for the user to specify what to do. After the decision step, a similar set of actions will be taken in a similar situation in the future, with a sort of machine learning emphasis here. Here's a little bit more of an in-depth view of the modes of operation. When the residents are not home, the butler switches to automatic mode. In this mode, it can still adapt to unexpected events. If something adverse happens in standby mode when everyone is gone, the butler will take appropriate actions and learn what may have went wrong, such as a door being left unlocked. So let's look at the picture to the left, which describes a more abstract view of the modes of operation from a more compartmentalized 5C architecture type of view. So we start at system initialization, where it grabs its predefined rules, variables, and basically its state from the last time it was operating. It then collects information from the physical sensors, followed by analyzing and aggregating data. Then it decides. It creates a hypothesis on what should be done next based on the current situation. It then uses physical actuators to respond to its current situation, and then it detects if there's any manual changes by the user, and it will then adapt. It will collect that data, and it will start the process over, regardless of whether there is information from the user or not. If there is, it will adapt, and if not, it will continue as it currently is under the settings it established. An example of the security agent's thread. At the beginning, the agent reads the current status for all the security nodes. It compares the current status with the last recorded status for all nodes in the agent's memory. If there's a change to the status, then the security agent's thread has completed. If there is not a change to the status, then it detects. If there is no change in the status, then the thread can complete. However, if something has changed, it will go ahead and read the sensors. The motion detector, the glass break sensor, the entry door detector, whatever detectors that a security system would use. These are examples. It sends this information to the butler if something is wrong with the sensors. However, if nothing is wrong with the sensors, it will retrieve user ID via a wristband or by face detection camera. If this is the case, and the user can't be detected, then it will notify the butler. However, if it can detect the user, the security agent will start recording video immediately. It then sends this information to the butler. At the end of any of these scenarios, it will update node statuses in agent memory. It will then end the thread. Here's an example of the lighting agent. At the beginning, it checks, is there any new messages in queue from the butler? If not, end the thread. If there is, however, then we need to read the command. There's a few possibilities that this command could be. For example, you could get a read status. It will then simply return information to the butler. It could have an off status. It waits for a set amount of time, and then it reads the new command. If the command is still to shut off, it will then shut off the lights, update the node status in the agent memory, and update the butler with its new information. Then end the thread. If the command is not to shut off, it goes back and checks for the command again. If it's turn on, for example, then it will check, is the command an unknown illuminance level value? If the command contains a known illuminance level value, then it will use the embedded light sensor. The agent reads the current illuminance level from its buffer. It will then determine whether it needs to increase or decrease the illuminance to a different level based on the command. Then it updates the node and sends the status back to the butler. However, if the illuminance level value provided by the command is unknown for some reason, then it turns the light level onto the initial level, unless there's some preferred information from the user specifying that they want a different initial level. It then updates the status with this information to the nodes and sends it to the butler. It then updates its nodes in agent memory and sends the status back to the butler. Here's a NetLogo home simulation. This is a piece of software designed to simulate designing a Internet of Things scenario from a somewhat cyber-physical systems perspective. Remember that cyber-physical systems is a very broad definition. In this NetLogo home simulation, you can see certain things are grouped into different aspects. You have the TV, the coffee maker, the sprinkler motor. You have bedroom lights, garage lights, kitchen lights, etc. All the lights are in one section. Some of the appliances are in another. You have door sensors, window sensors, all in a sort of security section. And you have a few graphs and charts looking at some of the watts for different power consumption statistics, shown in tables to the right of various appliances. The Setup button, which is labeled 1, presets the nodes in the home environment to the initial state. The Run button, labeled 2, is used to execute the software program in a continuous loop. The Standby Mode button, number 3, allows operators to choose between two types of configurations, the Active Mode and the Standby Mode. Because of the different procedures between each mode, we can choose the first mode when the user is at home. Otherwise, we can choose the Standby Mode whenever the user is away. By operating the manual mode button, we can select the manual mode of operation and the automatic mode of operation. The manual mode button represents what we have in our home and how we control the nodes in our daily life. In other words, this mode neither has any agents for each subsystem, nor an intelligent agent, nor a butler. Therefore, the control process for any node must be done by the user himself or herself through a direct interface. This allows the simulator to represent the status of the home when there is no smart home controller. The Auto Mode button represents the existence of an agent for each subsystem. The butler as the brain of the automated system, and the cloud as the storage backup. In this mode, the butler would take control of the nodes and make changes according to the predefined rules. However, it is important to mention here that if the user tries to change the status of any nodes, the butler should give the user the privilege to execute what the user needs and record the new behavior. Since the butler is tracking the user's behavior, the butler sees that the same action happened several times. Upon the same set of inputs or sensor values, the butler would adapt by building or editing the current rule for that status in the database that exists inside the butler. Using these different buttons provided in the NetLogo home simulation allows for a streamlined approach to simulating cyber-physical systems in our architecture that we have described in this presentation. On the screen, you can see that some of these appliances have been located in the simulation. So you can click on them and see their statistics. Here's a generic use case for a typical day. In the morning, the user's alarm goes off at 6 a.m. and the bedroom lights turn on. The user does his hygiene and breakfast routine. The system tracks the power consumption during the morning routine. The automatic mode learns from this and can efficiently allocate energy resources in the future. In standby, the butler acts autonomously, detecting any changes with sensors, like the broken window sensor and smoke detector. The butler can take the appropriate action if something goes wrong, like turning all the lights on, turning on the security camera, sounding an alarm, and calling 911. The butler can also track energy and water use by calculating the past and present usage statistics. The butler can help reduce resource consumption in the future. In conclusion, there is a huge demand for diversified large-scale cyber-physical systems for Internet of Things software. This could be applied citywide to the electrical grid and to manufacturing applications. These large systems have significant challenges: portability, timing, predictability, and integrity. In this work, a proposed design pattern helps to integrate solutions to the challenges with a focus on smart homes. The butler is a central unit which holds all the intelligence of the cyber level tasks. It communicates with subunits that interface groups of devices that assist the user. The butler is also connected to cloud level applications that can interface the smart home with larger scale smart entities. The next phase of the author's research is to utilize data gathered from a smart home to test machine learning for predicting user behaviors. This will further support the research into the autonomous abilities of smart homes. Thank you for watching this presentation. Everyone is invited to ask questions and propose ideas for the presentation in the Piazza forums.